Good morning to all of you. Today we are discussing about basics and what are the basics required to study about DC machines. Here, what are the basics we need to study about this? In order to function in the DC machines, we need to know about what is the Faraday's law. Because both generator and motor works on the principle of Faraday's law of electromagnetic induction. We have two types of laws, Faraday's first law and Faraday's second law. We need to know about what is the Faraday's first law and what is the second. And also we need to know about Lenz's law. After that, in order to finding the direction of individual EMF in DC generators, we are using the Fleming's right-hand rule. Similarly, in order to find out source direction, we are using the Fleming's left-hand rule. After that, we need to know about what is the electromagnetic force and magnetomotive force. These are the basic terms we are required to know about. Study the concept of DC machines. After that, we are going for DC generators and what is the principle of vibration. In order to construct the DC machines, what are the main parts? We will discuss about all these things today here. If possible, we can derive the AMS equation of DC machines. Here, first of all, we are discussing about classification of DC machines. DC machines means the machines which works on the DC supply, known as DC machines. Here we need to give the DC supply and the machines are works for DC supply. The DC machines are classified into DC generator and DC motor. DC generator is our first unit. DC motor is our second. So the functioning of motor is it takes mechanical energy as the input and gives the electrical energy as the output. So the case of this motor, we are taking electrical energy as the input and taking the mechanical energy as the output. These two both the machines, either DC generator or DC motor, so it's only the principle of Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. Here, depending upon excitation given to this DC generator, they are classified into separately excited and self-excited. Similarly, the DC motor are classified into separately excited and self-excited DC motors. Again, the field winding connected to the across the armature, they are classified into self DC generator, series DC generator, compound DC generator. Here, we are having two classifications similar to the difference. We will later discuss about all these things. What is the types of DC generators? Again, how we are classified into three types. Again, this compound generator classified into two types. Here, the function of generator. Generator is a machine that converts mechanical energy into electrical energy. Here, for the generator, we are given mechanical energy as input, we are taking the electrical energy as the output. But when you are coming to a motor, you are considering electrical energy as the input, mechanical energy as the output. Both are functioning vice versa. Motor takes electrical input and gives electrical mechanical output. And generator takes mechanical input, gives the electrical output. The energy conversion is based on the Faraday's law of electromagnetic induction. Energy conversion is based on the Faraday's law of electromagnetic induction. First of all, what is Faraday's law? Okay, Faraday's law consisting two laws. The first law describes how the induced how the induction of EMF in a conductor. And second law, what is the quantity? Second law quantifies the EMF produced in the conductor. First law gives how the EMF produced in the conductor. Second law gives how much of EMF induced in that conductor. So Faraday's first law says that whenever a conductor placed in a varying magnetic field, an electromotive force is induced. If the conductor circuit is closed, a current is induced, which is called induced current. Faraday's first law says that whenever a conductor placed in a time varying magnetic field, an electromotive force is induced. With the conductor having closed circuit, due to that induced EMF, we are having the flow of current, that current known as induced current. Faraday's second law says that the induced EMF in a coil is equal to the rate of change of flux linkage. The induced EMF in a coil, that is voltage, is directly proportional to the rate of change of flux linkage, d psi by dt, where psi represents the flux linkage. Psi represents flux linkage. Psi represents flux linkage. We'll see one video about this Faraday's law of electromagnetic induction.
We are going to discuss Faraday's law of electromagnetic induction. Let us take a simple coil. Let us connect one battery across it. Hence, there is a magnetic field surrounded.
When we are considering one coil and it is supplied with the help of one battery, due to the flow of electrons, they are producing one magnetic field around
Let
this
us take
coil.
another coil connected across a galvanometer as shown here in the figure. Now, we will hold the second coil nearer to the first coil. More specifically to say, hold the second coil under influence of magnetic field of first coil. Now, we can observe that there is no voltage appeared across the second coil. There will be no deflection in the pointer of the galvanometer. Although at that condition, there is magnetic flux linkage in the second coil from first coil, but no voltage induced in the second coil. Now, we move the second coil inside the influence of magnetic field of first coil. Now, we can observe that during movement of the second coil, the pointer of the galvanometer deflects. This indicates that some voltage has been induced across the second coil while the second coil was moving. Now, let us move the first coil, keeping the second coil stationary at its place. In that case also, we will observe that there is a voltage induced across the second coil. In this case also, the pointer of the galvanometer deflects. In first case, there was a flux linkage in the second coil from first coil, but no voltage induced in the second coil. In the second and third cases, there was still flux linkage in the second coil from first coil, but the flux linkage was changing due to movement of coils. So we can now conclude, whenever a coil or any other conductor comes under influence of changing magnetic flux, there is a voltage induced in it. The voltage induced due movement of the conductor or magnetic field is called dynamically induced voltage. We can create the same condition without any movement of either of the coils. In that case, we have to apply an alternating voltage across the first coil. This produces a changing flux. This changing flux will link the second coil, and for some reason there will be an induced voltage across the second coil. In that case, both conductor and magnetic field are physically stationary. The induced voltage in this case is called statically induced voltage. In all events, when there is a changing flux linkage, a voltage is induced. This phenomena was first observed by Michael Faraday, and he stated as a law called Faraday's first law of electromagnetic induction. Faraday's first law says when a conductor links with a changing magnetic flux, there is a voltage induced in it. Now, we will move the second coil faster inside the influence of magnetic field of first coil. We will see that during faster movement of the second coil, there is more deflection of pointer of the galvanometer connected to it. Same thing happens if instead of second coil, we move the first coil faster. So, when relative motion between magnetic field and conductor increases, the induced voltage across the conductor is also increased. The increase of relative motion between magnetic field and conductor means increase in rate of change of flux linkage with respect to time. Michael Faraday stated that in his second law of electromagnetic induction. His second law states the magnitude of induced EMF in a conductor is directly proportional to the rate of change of flux linkage with respect to time. If we observe the pointer movement of galvanometer during movement of the second coil or first coil, we will find that the movement of the pointer in one direction when both coils come closer, and the movement of the pointer in opposite direction when both coils go away from each other. When the coils come closer, there is an increasing rate of flux linkage, and when the coils go away from each other, there is a decreasing rate of flux linkage. Thus, the polarity of the induced EMF in a conductor depends upon whether the rate of change of flux linkage is increasing or decreasing. Now, let us come to the mathematical form of Faraday's law of electromagnetic induction. If there is n turns in second coil and rate of change of flux linkage with respect to time in second coil is d phi dt, then the induced EMF in the second coil is E equals to minus n d phi dt. Here, two things to remember. One, constant of proportionality is 1. This means EMF induced in a turn of coil is exactly equals to the rate of change of flux linkage with respect to time with it. 2. There should be a minus sign in the left hand side of the equation. This is to justify the Lenz law, which states that polarity of the induced EMF opposes its cause, which is changing flux linkage. Hope you got a basic idea of Faraday's law of electromagnetic induction. Thank you.
There is by reference flux, number of turns in the coil can be represented with N. N into 5 gives flux linkages. Now induced EMF is directly proportional to rate of change of flux linkages is equal to V equal to minus N into d5 by dt. Here the induced EMF opposes its rate of change of flux linkages, which can be represented with the help of negative sign, which not to satisfy the Lenz law. Now the Lenz law says that the effect opposes its cause, where due to rate of change of flux linkages, we are getting the induced EMF, where effect is induced EMF and cause is rate of change of flux linkages. In order to oppose the rate of change of flux linkages, we are getting the EMF in opposite direction, V equal to minus N into d5 by dt. Lenz law states that induced electromotive force with different polarities induces a current whose magnetic field opposes change in magnetic flux through the loop in order to ensure that original flux is maintained through the loop when current flows in it. Here, the Lenz law opposes its cause. We are having two types of induced EMF. When you are dealing with DC supply, we are having constant flux, and in order to produce EMF, we are having the place in the conductor. When you are having the constant flux and conductor and relative motion between these two, we are getting the dynamically induced EMF. When you are dealing with AC supply, we are having time varying magnetic field. Time varying magnetic field, because here the magnitude of voltage is constant with respect to time, but here the magnitude of voltage varies with respect to the time with frequency here. Here we are having a time varying magnetic flux and keeping the conductor stationary. Then we are getting the statically induced EMF. Is the EMF induced across the conductors available inside a time varying magnetic field. Both conductors and magnetic field seem to be stationary. Here we are having one conductor. It is supplied with AC. Then we are getting time varying magnetic field. We are having stationary conductor. Here we are connecting wall. Due to this time varying magnetic field, in this we are producing the self-induced EMF. Here we are getting the mutual induced EMF. Mutual induced EMF. This is occurs in case of transformer. When dynamically induced EMF, self-induced EMF and mutual induced EMF. Dynamically induced EMF means here we are having one coil is supplied with one battery or DC supply. Then we are getting constant flux. Here we are placing one more conductor. When you are keeping moving this conductor or moving this conductor, either moving any one of these two conductors, we are producing the dynamically induced EMF. It is of course this type of EMF induced in the case of DC generators. In this type, the magnetic field system is kept stationary and the conductor is moving, or the magnetic field system is moving and the conductor is stationary. Once the following either two of forces, conductor steps across the way. These are some basic definitions. What is the electrical flux? The total number of electric field lines passing given area in unit time is defined as the electric flux. Here, the consider one conductor and excited with help of DC supply. Then we are getting this coil becomes the electromagnet. Here we are having the particles. How many number of electric field lines passing in given area in the unit time is defined as electric flux. Electromotive force. The force which is required to movement of electrons known as electromotive force. The force which is required to keep electrons in motion. To convert mechanical energy or other form of energy into electrical energy is known as electromotive force. This is the magnetic motive force means the force which is required to flow of flux or production of flux in a magnetic circuit is called as magnetic motive force. It can be represented with the help of ampere terms. It is measured with the help of ampere terms. Number of turns in the coil and what is the current flowing in the. In order to find out the direction of induced EMF, we are using the Fleming's right hand rule. Fleming's right hand rule. With the help of this Fleming's right hand rule only, we can find out the direction of induced EMF. Shows the direction of induced current when a conductor attached to a circuit moves in a magnetic field. It can be used to determine the direction of current in generator windings. When you are keeping the three fingers of right hand 90 degrees to each other, the thumb represents motion of the conductor, the forefinger represents direction of field, and middle finger represents direction of current. Direction of current. Your consider is all about Fleming's right hand. When you are keeping the right hand three fingers 90 degrees to each other, thumb represents motion of conductor, forefinger represents direction of field, middle finger represents direction of current. You have seen here, according to Faraday's law of electromagnetic induction, in order to produce the EMF, we are required magnetic field. When you are given these excitation to the field winding, it becomes as electromagnet. And in this electromagnetic field, we are placing another conductor having some relative motion between these two. A uniform magnetic field, system of conductor, and relative motion between the magnetic field and conductors. Then we are getting the either dynamically induced EMF or statically induced EMF. The magnetic field may be either permanent magnets or electromagnets. Permanent magnets means it constantly has producing certain amount of magnetic lines of force, not Coulomb force by having. Electromagnetic means they are considering one coil and given supply to this coil, either to DC or AC. When given supply to this field winding, it becomes as electromagnet. Conductor. Conductors either maybe we are using copper conductors or aluminum conductors. The relative motion can be calculated with the help of either prime mover or turbine IC engine. Prime mover means for the generator, always we are using motor as the prime. Generator motor shaft and rotor shaft both are connected with the help of shaft. Here for the motor we are given electrical energy as the input. We are taking the mechanical energy as the output. This output of the mechanical energy will be given as centrifugal motion inverter. Here we are taking the loads. Here we are taking the electrical energy. Right. For the generator, motor is the driver. Now generator principle. Here generator takes mechanical energy as the input and putting the electrical energy as the output. Electrical generator is a machine which converts mechanical energy into electrical energy. The energy conversion from mechanical to electrical is based upon the principle of Faraday's law of electromagnetic induction. Principle of the prediction of dynamically induced EMF. Dynamically induced EMF means we are having a time invariant flux and conductor in motion. Conductor in motion. The help of time. Whenever a conductor cuts magnetic flux, dynamically induced EMF is produced according to Faraday's law of electromagnetic. The EMF causes current to flow in the conductor when the circuit is closed.